Hello, everyone. So what we're going over is some basics of electricity rates. I know there are some really crazy things out there. I did a little bit of research on this yesterday, looking for, because I was doing some slides and things like that, putting this together, and I found things I've never even imagined. No one's ever mentioned these things to me before. They're crazy, and I'll show at least one of them to you a little later today. Or, well, we don't have a lot of time. But this is what we're going over. So we're starting really simple, and then we'll get a little more involved. I start simple just because I don't want to lose anyone in this very first concept, kilowatt hours versus kilowatts. If you don't have this, then a lot of what we talk about later is going to be just a mishmash. It's not going to make any sense. All right, so we'll talk a little bit about blended rates and why it's a good or bad idea. I thought this might be interesting. Actually. And then we'll talk a little bit about modeling rates, what a pain in the neck it is, and then we'll go over some of these concepts. And that's really what this was all about. Okay, so energy versus demand. So I think you know, or most of you know, that there are demand charges and there's energy charges. But I think it's important for you to know clearly, at least what the difference between the two of them are. The way I describe it is energy is, it's an amount. It's how much of something you use. So another word for that is consumption. How much did you use as energy? And demand is a rate. It's the fastest rate at which you are using energy. At least when it comes to electricity. Gas is a different story, and it's rare you find utilities who talk about gas demand. So we'll just stick with electricity while we're talking about energy versus demand. So again, demand is the fastest rate at which you're using electricity. Often what utilities will do is they'll have a sliding 15-minute window, and they'll average the highest rate of usage over those 15 minutes throughout the whole billing period. And at one point in the whole billing period, you are using electricity, a lot of it. And that is going to be the 15-minute period that sets your demand. That's kind of how it works. I have an analogy, and that is of a rental car. If I was renting cars, I would charge based on the number of miles driven, which is what they used to do in the old days. And I would charge based on the top speed at which you drove. So I put a special meter in your car, like a demand meter, which would measure what's the highest miles per hour you went. And I would penalize you for that as well. Because people like that, I don't want them driving my cars if they're going 100 miles an hour. Okay, that's kind of like what the utilities are doing here. So an analogy here is energy is like miles driven. Demand is like the highest miles per hour driven. Okay, that's the first concept. Now we can get into something a little more interesting. Okay, blended rates. Well, this is also maybe very simple, but I wanted to go into it briefly. When I use the word blended rates, basically what I mean is we're just looking at the total dollars and the total kilowatt hours, or the total dollars and the total gas usage. I don't care how much is tax. I don't care how much was demand. I don't care about any of that. I just look at total dollars, total kilowatt hours, divide one by the other, and you get dollars per kWh. That's what I mean by blended rates. This is, as most of you know, this is the most common way ESCOs measure energy savings, or at least, let me say it different. The most common way that they apply costs to their kilowatt hour and therm savings numbers. They don't all do that, but this is the most common way. And there's a lot of reasons to do it that way. Okay, so there's different ways you could apply these rates. So one was, which we just talked about, which was the blended rate. And I mentioned that was really simple, and we'll explain why it's a good idea in a minute. But the one concept I want to explain right here is when you're doing a blended rate, you use the current year's blended rate. Okay, what I mean is if your base year was, let's say, the year 2010, and the current year is 2018, you use the rate from 2018. Okay, you don't use 2010's rate for the old usage and 2018 for the new. We use the new rate for both. Now, I understand a lot of ESCO contracts have these minimum charges, and we're going to use the maximum of the current rate or the rate time assigning a contract. We're not going to talk about this. This is mostly a rates class, but I understand that that is also something to be concerned about. Okay, there's another way of doing this, which is what I think you should I mean, really, if you had the time, you should do, and that's to model the rates. And that means to read the rate tariffs and to understand how the rates work and apply that to your energy savings numbers. We're going to go into that a little bit later, but that is really ideally the best way to go about this. There's another way, which is called marginal rates, and that's more accurate than blended rates. And I think I'm going to talk about that a little bit later, but I'll just mention it once here. And a marginal rate, let's say you had a tiered rate. It's 10 cents for the first 1,000 kilowatt hours, 9 cents for the next 1,000, and everything else is 8 cents. And let's say you know that they're using 50,000 kilowatt hours, so most of their usage is 8 cents. Well, then you're going to use the last tier when you're measuring savings, because you're going to save energy on the last tier. They're never going to get into the first two tiers. I don't think you're going to save, 95% of their usage. So what you would use, the more accurate way to do this, rather than blended rates, is to use a marginal rate. Look at the last tier, and that's what you're using. But it gets a little more complicated when you have demand and all of that. So it's not as simple as I say. And then you can always just pick some arbitrary rate, and that's what some folks do as well. So here is a case of blended rates and applying the right cost. So I have before and after. That would have been like the 2010 and the 2018. Here's something where you save some energy, save quite a bit, and it looks like the rates went up. So it was 10 cents a kilowatt hour, now it's 12 cents. So here I calculate the savings, it's pretty easy. I have two ways of calculating dollars here. So let's see which one's right. The first one, what I did was so there's these two savings. So I have this 10,000 minus 7,200. That's because I got 10,000 from the before and 7,200 from the afterwards. And you get savings at 2,800. That's really not the right way to do this, okay? The right way is to apply this 12 cents, because this is the current rate, to the before numbers. So it's 12, so that's 12 cents times 100,000 is 12,000. So it's 12,000 minus 72 is 48. That's the right way to do it, okay? Because it's when you're measuring savings, you're using the current rate, because this is how much they would have used. They would have used 12,000, not 10. So why not use blended rates? Well, I just explained how blended rates works kind of good. The reason why you use them is, well, I know how it is. Guys that work for ESCOs are busy. So that's number one. You don't have a lot of time. And blended rates are easy. In fact, you don't have to do anything. It just does it by itself. So that's good. It's easy to explain to management, easy to explain to clients. Excel does this. Anything does this. But there's problems. And so here's an example. I'm going to explain really briefly what thermal energy storage is. Thermal energy storage basically is, the whole idea is you have this cool, let me back up. This is what the top pattern here, this is what a typical building might use. They have their base load, they turn on their lights, computers, or whatever, their fans during the daytime, and they do cooling on top of it. And but what thermal storage does is it basically does the cooling in the night times. So they're what they're doing instead is they're let's say balancing the load out, so we don't have these high peaks, which is what we would call the demand. So they're going to use the most energy, maybe 3 o'clock in the afternoon, and that's going to set their demand. Well, now 3 o'clock in the afternoon, it's only 800 kilowatts, not 1,500. Okay, so that's kind of what thermal storage does. I'm not explaining the whole technology and all that stuff, but that's the idea. It's just shifting the load. So here's that same example, or a similar example, I guess. Thermal energy storage, it involves pumping, making chilled water at nighttime. And then you pump it and you store it in a tank, and then you got to pump it back. And it might actually, and there's losses while you're, the chilled water or the ice is being stored in a tank, and it could melt. So, there could be losses. So there's energy that's wasted. And so it's not always true, but sometimes thermal energy storage will actually use more energy. So before we were using this, after we're using this, but the rates went down. So before it was 10,000 and after it was 84. Well, they went down because now we're not using all peak energy usage. We don't have that high peak demand anymore, and we're using a lot of off-peak energy. So it's going to be a lower total cost, even though the usage went up. So, but if we did this with blended rates like I showed before, we had we had Oh, we have negative use. That looks terrible. So there's two ways to do this. I can look at the cost before, the cost after, so that this one and that one. So 10,000 minus 8,400, and I end up with a little bit of savings. Or I could do it what I said was the right way, where we use the blended rate from after, 8 cents per kilowatt hour. And I think I made a mistake there. I think this should be $8,000 minus 8,400, and I end up with negative $400. So I end up with a loss. Well, that's what blended rates will do. This is an extreme example, but it doesn't work, okay? So blended rates here is a disaster. The right way to do this is if you modeled the rate correctly, you would see the real savings that happens. Okay, let's get into this. I guess the first concept, and that is time of use. This is pretty simple. This is what PG&E at least used to look like. I think it's a lot more expensive now. But what you can see is we have in the summer season, we have a peak, which is in the afternoon, and we have a part peak, and then we have off peak, which is at nighttime, okay, and weekends. And then in the wintertime, at least for PG&E, we don't have peak. We just have part peak and off peak. But at these different time of use periods, we have different rates. The idea is it's more expensive when everybody needs it. And when no one needs it, it's a lot less expensive. In fact, I've heard that in El Paso, it's gotten, because of the windmills and all that, they've actually had electricity being negative. They actually pay you to use it because they have too much on the grid. But that would be during off-peak. Okay, so here is another look at that time of use where we have on-peak, mid-peak, and off-peak. It might be different hours, but it's just an idea. I took it off the web somewhere. So I just wanted to show you, I forgot why I was showing you this, but I guess I was showing it to you because the whole idea of thermal energy storage was load shifting, and I was basically taking away a lot of this on-peak and some of this mid-peak and energy usage, and I was putting it into the off-peak where it was cheap. So, okay, blended rates. More issues. So if you've got a tiered rate, which I mentioned before, which energy tier are you going to save in? Well, you're probably going to save in this last one. That's what I was mentioning before with called marginal rates. And so what you might choose to do if you had a simple Excel calculation is just use marginal rates instead of a blended rate. Let's say your blended might be something like 12 cents per kilowatt hour. But instead, what you could use is the marginal rate, which is this one, 10 cents a kilowatt hour, because that's where all the savings is coming from. None of it's coming from here or there. Okay, so blended rates, let me go back. They will overestimate the cost savings. Let me take that back. When you have a tiered rate, blended rates will overestimate. So let's see, let's say we put in a new chiller. This is interesting. You put in a new chiller, we have a time of use rates. So you're going to save all your energy here in the red zone on peak and a little bit on mid peak. And let's say none on off peak. Okay, if you use blended rates, you're going to use the average of all this usage, and it might be somewhere like, I don't know, 7 cents or something, or 7.5 cents. But most of your savings was when the usage was 9 cents a kilowatt hour and 8 cents. If you're using blended rates when what you're doing is you're cutting demand, you're going to end up under predicting cost savings. Okay, so blended rates doesn't work for you that way either. But there's these certain rules that you can kind of, I mean, they're rules of thumb and they're not always right, but this is one of them. So with tiered rates, blended rates is going to overestimate savings. With time of use, if you are doing, saving, you're cutting demand, then it's going to underpredict cost savings. And let's say you wanted to do something to reduce energy usage at night. So you're going to turn things off, do a night setback, or lighting sweep control, that's turning off lights. Then blended rates is going to overpredict your cost savings because most of your savings is going to happen during off peak, and your blended rates up here, it's like 7 cents or something. So that's going to overpredict. So those are, what I'm trying to explain is blended rates kind of sucks. It can give you really bad results, but usually just the wrong ones. Sometimes it's good enough though. All right, let's get to it. So we're here to talk about tariffs. So the way I go about modeling rates is first you go online and you look up the utility. I usually type in the word tariff book. It seems to work for a lot of utilities. They seem to call it tariff book. And so then you'll get something like this with all the electrical rates or gas rates. The tariffs often, when I say they're wrong, the dollar amounts are usually right. It's just that they're missing things. Or maybe it's in a different section. I don't know about the word wrong. Actually, in some cases, they have been wrong, where the wording is funny. So sometimes, you'll see rates, I think you'll see this next one right here, where it's really simple. It's in a table. Well, I don't think there's anything wrong there. But sometimes they'll describe all of this in a paragraph form. That's where things get funny. But anyway, this rate modeling can be really frustrating because you try to model everything. You've done everything right. You do it in Excel even, forget metrics. You do it in Excel because then you know that you're doing everything like you think you should, and it's still wrong. So then what you have to do is you got to call the utility. And those people who answer the phone, they often don't know very much. And I've found that if you act like you're a smart energy analyst or energy engineer, they don't want to talk to you and they don't want to help you. At least that's been my experience. So I often act stupid. And I just, act like I don't know anything. I'm just helping and I don't know. Can you help me? And then they actually help. And helping means they usually refer you to someone else who knows. These tariffs have a lot of pages and you got to sort through it all, find what's important. And this is basically the important stuff, something like that. Now, a few concepts, bundled and unbundled. You'll see that, in fact, I think this last one, I don't know if this had it or not. Let's see, it does not. So these are actually bundled costs. Okay, bundled means that in fact, do I have it? Yeah, here's unbundled. Unbundled means, well, here's the transmission cost, the distribution, and gosh, I don't know what any of these things mean, but there's all these different costs and you add them all up. This is the bundled amount, this total. But when they unbundle it, it's then you can see, well, how much cost all these different components and taxes and everything else is. Unbundled is also useful if you have a different supplier than the utility that's distributing the electricity. Then unbundled works because you have a generation charge, which is here. And then this is the transmission stuff. But that's that concept of what is bundled, unbundled. Another one, I don't know if this is all over the country or maybe just PG&E, but we have firm and non-firm. Firm means they're going to supply the power no matter what, unless there's a hurricane. Non-firm means, well, maybe we won't sometimes when it's a little bit too hot and everybody else needs power. We're going to cut it off for you, and it's a lot less expensive. So non-firm is cheap, but it means they might turn the power off on you sometimes. Actually, for some entities, if they've got backup generators, I don't know, might be the better way to go. Might be a nice ECM for you. Okay, another concept is secondary, primary, and distribution. What this is about is where are you getting your, at what voltage are you getting your electricity at? So most folks are getting secondary power, and oh geez, it's not a very high voltage. And then, but some organizations like, big hospitals or campuses or certainly factories, they're going to have transmission lines. They own their own transmission lines, or maybe the utility does, but then they're going to be getting their power, and the transmission lines actually are on their property. I'm sorry, I forgot what the word is. So anyway, it is like all this power stuff, and they have it in their yard and on their site, and it's like a substation. That's the word. Transformers and substations, and they have that, and so they get power that's delivered to them at a higher voltage, and as a result, they end up paying a lot less power. Okay, tiered rates. We talked about tiered. This is pretty simple. I don't think there's much of a concept there, but here is a little bit harder of a tiered rate. In fact, I'm not going to go over this, and some of you in my class have seen this before. But this is I'll just show you, it's a little more complicated. So here they have these kilowatt hour per kilowatt billing rates. Oh God, I don't even want to go into that, but let's just say the tiers can be a little more confusing. And I will go into what this kilowatt hour per kilowatt means in just a minute. But here's the one that got even harder. This was crazy. So I just want to look at this again, just to look at it. So these guys had summer, winter, and then they had transition periods, which are like spring and fall, I suppose. But check out, they've got the 9.2 cents, that's easy. Plus they have these 3 blocks. It's crazy. All right. And that's totally crazy. I've never had anyone come to me and, with a metrics question saying, how do you model this? I guess it's because no one's modeling rates, but or not many of you are, but oh my gosh, that's tough stuff. All right, so let's talk about this load factor rate stuff. So you're going to see some rates out there that are like, where the tiers are in kilowatt hours per kilowatt, or they also call it hours use. So instead of saying 10 cents for the first, they might say 10 cents for the first 50 hours use. They mean the same thing, okay? And the way to do this is, it took me, I think, 2 hours to figure this out the first time I did it. So it says 50 kilowatt hours per kilowatt. So what I do is I take this 50 and I multiply it by my demand. So 50 times my demand, that's down here, 50 times my demand, that's going to give me 5,000. I think that's right. And so that is the tier size in kilowatt hours. Okay, so that's what this means. If my demand was, let's say, 1, then my tier size would be 50. Be the first 50 kilowatt hours would be 10 cents per kilowatt hour. That's how that works. Oh boy, but the first time you try to figure that out, if someone like me didn't give you a hint or someone else did, didn't, maybe, you guys are smarter than I am, but I was confused. All right, fuel adjustments. So some utilities they'll give you, they'll have all these, rates and all these costs for, energy and demand and all, but they also have these monthly, or maybe they're by billing periods, or maybe they're even by quarter, but they have these charges that keep changing all the time. And here's one where they have a fuel adjustment, where every month is different, and it's based on the cost of, in Hawaii, it might be based on the cost of, I don't know, was it LPG or diesel or something like that, whatever they're burning to generate electricity. That's what the fuel is. Or maybe if they have a lot of gas turbines, it depends on the price of natural gas. So sometimes it's negative. If the natural gas or the LPG or whatever is cheaper than usual, then they'll take money off of your rate. Sometimes it's positive because the gas that month or billing period was more expensive. So that's what a fuel adjustment is. But there's, these rates, these guys, they just tack on more and more. I mean, it's not like they're tacking on stuff, but they're just, they have all kinds of charges and stuff. God dang, rate modeling is just a headache sometimes. Yeah, it is. But okay, another concept: metered demand versus billed demand. So metered demand is whatever the utility measures. We talked about demand, that's the highest speed that you're using power, right? Maybe in a 15 or 30 minute window. Well, so metered is what they measure. The billed demand is what they charge you for. That's different. So a lot of utilities, they'll bill you for whatever they measure, and that's that. But some of them will have all these other things like, well, there's a minimum demand, or maybe you have a contract demand of something, or you got ratchets or power factor. There's all this other stuff. And they'll say, whatever's the greatest of all these, that's going to be your billed demand. And that's what we're going to bill you on, okay? They also have these things called credits, and they're often demand credits. So like if you do, let's say you put in a electric hot water heater, then they'll give you a credit for, based on how big the heater is, they'll take a few kilowatts off of your bill. So it can go up. The bill demand can be more than meter demand, or it can be less. A contract demand, that is, sorry, I just took this definition off the internet. So different customers are assigned different contract demands by some utilities in some rate classes. Okay, it's not everywhere, it's not here, but that's the amount of power that they agree to have available. I guess that's what it says at all times. And sometimes this contract demand is going to be part of that calculation that determines what your bill demand is going to be. Here is a case, I don't remember what utility this was, but they're saying it's $10.61 per kilowatt by which the on-peak to milling demand exceeds the on-peak contract demand. So it's an extra 10.61 if your demand is higher than contract demand. So that's another case of using contract Ratchets, here's a case of a ratchet. It says it's going to be the higher of, I don't know what NCP means, and I don't want to look it up, but it's the kVA. We'll talk about that in a minute, but that's like kilowatts. So it's going to be the higher of the kVA for the current month, or 80% of the highest monthly in the last 11 months. That's a ratchet. I think of a picture right here. So this is one where I have 85%. So let's say, so your meter equals the build, except for we have this ratchet clause in here. It says, well, yeah, but we're going to look at 85% of the highest demand of the last 11 months. And whatever that is, we're looking at that or your current demand, whichever is greater, that will be your build demand. That's called a ratchet. Okay? Some people call them rolling ratchets. Okay. Oh, hey, thank you, Marco. NCP, non-coincident peak. Very good, Marco. Thank you. Power factor. Power factor is, I have a mechanical engineering background, and power factor was always confusing for me, but I think I finally figured it out. So basically, so it's this kilowatts is, that's what generally you're usually being billed on. Sometimes you're billed on kVA, but usually it's kilowatts. This reactive power is basically wasted power. I think my next slide, well, my next slide, I'll show this to you. But this power factor is just a ratio of kW to kVA. Okay, but I have some analogies. I think you've all seen this beer analogy before. Some of you have. So let's say you, I charge you for a glass of beer. I'm at a keg party. You get one glass of beer, and you're kind of an idiot, and you end up with half foam and half beer. So the foam is kind of waste. And that is kVAR, okay? And beer is what you really wanted. You really weren't interested in the foam. In fact, you might dump it out and then just get to the beer, because the foam's usually nasty to drink anyway. So, but this is the stuff you need. This is the stuff that runs your power or your equipment, and this is what people pay for mostly. But the utilities will actually bill you for power factor, and that's the beer over beer plus foam, and it's just a percentage of how much of this stuff they develop, or how much of the stuff in the glass is actually good as beer. And I think, yeah, so, but this analogy doesn't really work. So it's because if I charged, it would work like this. If I charged 50 cents per inch of beer, and then I charged 20 cents per inch of foam, that's how the utilities do it, okay? So then this analogy works. I can't just say you're an idiot, and you put in half foam, half beer, therefore, well, that's your problem. No, that's not how it works. This is more how the utilities work. Okay, power factors are typically, I don't know if I have that in my next slide. Oh, I do. So they're usually between 0.7, 0.9, and anything above 0.75 or 0.8 is pretty good. They often will charge you below 0.8. Yeah. Now, what causes bad power factors? It's stuff that you have in your own facility that actually is causing it, is causing this foam to appear. It's just like the idiot who can't get the beer in his glass without the foam. It's the same. You end up with certain types of equipment in your plant, and then you end up with bad power factor. Okay, and there's ways to correct it with putting in capacitors and all of that, but we're not going to talk about that. But it's actually your fault that you have bad power factor, not them. Oh, look at that. I managed to cover everything. So I guess I made it through. So I'm actually, that was a lot of stuff. I hope this was valuable to you, and I hope Tyler's around listening. So let's see if I have any questions.
Why is John not looking older? Yeah, that's a tough one to answer. Oh, why is he looking older? Oh, that's an easy one. Okay, yeah, no problem, Crystal. We will definitely send the slide deck out to everybody.
Thanks, everybody.